A spacecraft blossoms in the void, its wings unfolding from a tiny, silent seed. This is the Orbital Origami Revolution, a complete transformation in how we construct machines for space. We are entering an age where satellites and stations fold themselves into existence, blooming from incredibly dense packages into enormous, working structures. By the end of this, you will understand how this single idea is shattering the fundamental limits of space exploration. We will uncover how metal can remember its shape and what ancient art has to do with tomorrow's starships. What do you believe is the ultimate limit for what we can build among the stars? A child's paper crane holds a secret geometry that now echoes in the void. That simple, folded form is a blueprint for cosmic engineering. The same principles that turn a flat square into a delicate bird are being used to design machines that can survive the violence of a rocket launch and then blossom into vast, intricate structures in orbit. This is the core of the Orbital Origami Revolution. It is a direct answer to a problem called the tyranny of the rocket fairing. A rocket's nose cone, the fairing, is only so big. For decades, the size of every satellite, every telescope, every piece of hardware we sent up was brutally limited by that single measurement. We had to design everything to fit inside that cramped, cylindrical space. But what if you could design a satellite the size of a tennis court to fit inside a barrel? Origami provides the answer. By meticulously engineering folds and creases into the very fabric of a structure, we can pack it into an astonishingly small, dense package for launch. Once it reaches the calm of space, a simple command can trigger its transformation. It unfolds, deploying itself into a form that is dozens of times larger than the container it arrived in. This is not just about making things smaller for launch. It is about making things bigger in space. It unlocks the potential for massive solar arrays that power entire orbital factories, for enormous telescopes that can see the atmospheres of distant worlds, for habitats that offer real room to live and work. This beautiful marriage of an ancient art and cutting-edge engineering is solving one of spaceflight's most fundamental constraints. We are now able to send our biggest ideas into the cosmos in remarkably small packages. The journey from delicate paper to hardened space-grade material is a story of convergent innovation, a path that leads us directly to the miraculous substances making it all possible. The magic behind this cosmic unfolding lies in materials that remember. Think of a tightly coiled metal spring, holding the perfect image of its original, extended shape and straining to return to it. This is the essence of shape memory materials, the first critical innovation making self-folding space machines a reality. These are not ordinary metals or plastics. They are advanced polymers and composites, engineered at a molecular level with a permanent memory of a predetermined shape. On the ground, we can fold and pack them into incredibly dense packages, locking them into a temporary, compact form. But once they reach the void, a specific trigger sets them free. That trigger could be the gentle warmth of sunlight bathing their surface, a small electrical current sent from the satellite's computer, or simply the release of a mechanical latch. When activated, the material undergoes a dramatic internal phase change. Its molecular structure shifts, and with a quiet, powerful certainty, it reverts to its memorized shape. This is not a slow, weak movement. It happens with remarkable force and precision, unfurling a solar panel boom or deploying a massive antenna reflector without a single motor, gear, or explosive bolt. This elegant process slashes the mass of the spacecraft, eliminates countless potential points of mechanical failure, and turns a complex, risky deployment into a simple, reliable event. It is the physical heartbeat of the orbital origami revolution. Yet, for these smart materials to perform their dance, they require an equally intelligent blueprint, a set of instructions written not in words but in geometry. This intelligence moves from the material itself to the very geometry of its design. At the microscopic scale, engineers are not just using materials, they are composing them, building substances atom by atom to achieve the impossible. This is the frontier of programmable matter and metamaterials, the second pillar of our unfolding revolution. Think of a fabric woven not with threads, but with tiny, intelligent cells. Each microscopic unit can receive a signal, causing it to expand, contract, or twist. When thousands of these cells act in concert, the entire sheet of material comes alive. It can fold itself along invisible, predetermined lines, or even more remarkably, it can change its shape completely after it has already been deployed. This transforms a simple structure into a dynamic machine. A single satellite wing could alter its form, one moment acting as a high-gain antenna for broadcasting, and the next moment reconfiguring into a dish designed to listen to faint cosmic whispers. A solar sail, that elegant spacecraft propelled by sunlight, could actively adjust its curvature to steer more efficiently, turning a passive sheet into an intelligent sail. This is the ultimate evolution, a shift from a machine that unfolds once to a machine that can adapt, morph, and respond to the challenges of space in real time. The line between a rigid structure and a flexible mechanism completely dissolves. But how do we command this intricate dance of a million microscopic parts? The folding instructions are no longer just creases in metal, they are lines of digital code. This brings us to the silent, sophisticated conductor of this entire cosmic ballet, the software that breathes life into the fold. Every single fold is a calculated move in a cosmic dance, choreographed long before the material ever feels the cold of space. This intricate planning happens in the world of computational origami, a field where brilliant algorithms replace the artist's hands. Here, the goal is to find the most elegant and efficient path to transform a simple, flat sheet into a staggeringly complex three-dimensional object. Engineers feed their grand vision into sophisticated software, which then models the entire life of the structure. The program simulates the physical stresses on every crease, the precise kinematic path each panel will travel as it unfolds, and how all these movements interact in the silent, frictionless environment of a vacuum. These digital models must anticipate problems human eyes would miss, like stiction, where folded joints might stubbornly stick together, or the way a large panel might wobble as it deploys in zero gravity. This virtual testing ground is where potential snags and catastrophic failures are caught and solved. The software runs through thousands of deployment sequences, tweaking angles and adjusting fold patterns until the unfolding is not just possible, but perfectly reliable. The final digital blueprint is far more than a simple design. It is a predictive movie of the structure's entire existence, from its densely packed launch state to its final, magnificent operational form. It is the birthplace of certainty in an inherently uncertain endeavor. Yet, this flawless digital plan must eventually meet the harsh, unforgiving reality of space, a handoff that depends on highly specialized deployment mechanisms. The transformative power of a coiled spring is the hidden force behind many of these cosmic unfoldings. This principle, known as strain energy deployment, is one of the most elegant and reliable methods we have. Picture a long, slender boom for a solar array, carefully folded and compressed against its will. It is like a tense metal ribbon, holding its breath, its own material yearning to spring back to its straight, natural form. This stored potential energy is its fuel for deployment. The release is often startlingly simple. A tiny electrical pulse might melt a special wax actuator or heat a shape memory alloy pin that then retracts, acting like a latch on a gate. The instant that latch is undone, the stored strain energy is unleashed. The structure snaps into its intended shape with a decisive, powerful motion. This entire process requires no motors, no gears, and no complex machinery. The power for the transformation is baked directly into the physical design of the component itself. This beautiful simplicity translates into exceptional reliability, a non-negotiable requirement for systems that get only one chance to work. A satellite's primary solar arrays, the very things that give it life, or its large communication antenna, its voice to Earth, often rely on this trusted high-force method. Yet, for all its brute force elegance, a spring-powered deployment is a one-time event, a single, magnificent gesture. Some missions, however, demand a more nuanced performance, a sequence of delicate movements that require the gentle, precise touch of a different kind of machine. For missions where a single, powerful snap is not enough, a more delicate touch is required. When an instrument is as fragile as a soap bubble or its position must be perfect to within a hair's width, engineers turn to motorized actuation. This is the realm of the cosmic watchmaker, where miniature, radiation-hardened motors and intricate gearboxes are placed with surgical precision at the key joints of a folding structure. These are not brute force mechanisms, they are the conductors of a slow, deliberate symphony of movement. With each tiny, controlled rotation of a motor, a vast, gossamer thin membrane for a solar sail can be tensioned without a single tear. A massive radio telescope, its surface precision ground to microscopic tolerances, can be coaxed into its perfect parabolic shape, panel by careful panel. The greatest strength of these motorized systems is their intelligence and repeatability. Unlike a one-time strain energy deployment, a motor can be reversed. A panel that does not latch correctly on the first attempt can be gently folded back and then redeployed. A communication antenna could subtly adjust its angle days or even years after its initial unfolding to maintain a perfect link with Earth. This introduces a powerful layer of adaptability and redundancy, turning a static structure into a dynamic one. Of course, this precision comes at a cost. Every motor, every gearbox adds mass and complexity, and each one is a potential point of failure that must be rigorously tested and shielded from the harsh environment of space. The choice between the simple, robust spring and the sophisticated, adaptable motor is one of the most fundamental decisions in mission design, a constant balancing act between raw reliability and graceful control. Yet, whether driven by stored strain or a whirring electric motor, these individual mechanisms are merely the muscles. To create a truly intelligent, self-assembling machine, they must be wired into a nervous system, guided by a brain that can sense its own state and correct its own mistakes. This intricate dance of unfolding parts relies on a deep, embedded intelligence within the machine itself. A self-folding spacecraft is not a collection of independent actions but a single, cohesive performance, a symphony of interconnected systems working in a meticulously choreographed sequence. The deployment is a chain reaction, a cascade of cause and effect where the successful completion of one movement directly enables the next. Imagine a line of dominoes, each one falling only after the one before it has cleared the path. In orbit, the release of a primary structural boom might create the physical space needed for a secondary latch to disengage. That latch, in turn, could unlock a mechanism that allows an entire solar panel wing to gracefully rotate and click into its final position. This sequential logic is hardwired into the very bones of the spacecraft. through a network of mechanical interlocks, electrical sensors, and software commands. There is no room for ambiguity. The system is designed with multiple redundant triggers and fail-safes, so if one pathway is blocked, another can be activated to ensure the entire, vital process completes successfully. This brings us to the critical discipline of systems integration, the art of ensuring that all these interdependent movements flow together without conflict. Engineers must solve a high-stakes, three-dimensional puzzle. They must guarantee that a panel unfolding from one side of the spacecraft will not, under any circumstances, snag on a wire harness or collide with an antenna deploying from the opposite side. They must model how the shifting center of mass affects the satellite's stability during the entire sequence, and how the new, deployed configuration will handle the extreme temperature swings between sunlight and shadow. Every piece must fit perfectly in both its tightly packed launch state and its final operational form. Witnessing this seamless, autonomous ballet from the vantage point of mission control is a breathtaking testament to human ingenuity. We can now watch this spectacle unfold in real time, verifying every step of the complex transformation with advanced onboard cameras and sensor data. This final validation is the crucial capstone, the moment of truth that proves our digital dreams can survive and thrive in the harsh reality of space. 1,000 kilometers above the Earth, a machine completes its silent transformation. But how can we be sure every latch has clicked into place, every panel has locked into its final position? The answer flows through a stream of data, a digital pulse sent back to mission control that confirms a successful rebirth. This is the phase of on-orbit validation, a critical final exam for the entire folding process. On board the spacecraft itself, a network of tiny, vigilant sensors acts as its nervous system. Micro switches no larger than a fingernail report the satisfying click of a joint reaching its final stop. Strain gauges measure the subtle tension in a newly deployed boom, confirming it is holding its shape under stress. Potentiometers track the exact angle of a rotating solar panel, providing a precise digital readout of its position. This constant stream of telemetry data is the spacecraft's real-time health report, a detailed narrative of its unfolding story that engineers on the ground monitor with intense focus. Yet, sometimes data is not enough. We need to see it with our own eyes. For that, we deploy cameras directly onto the spacecraft structure. These are not simple webcams. They are ruggedized, radiation-hardened eyes in the void, positioned to capture the most critical moments of the deployment sequence. The footage they beam back is both breathtakingly beautiful and immensely valuable. It offers undeniable visual proof that a vast antenna has unfurled without snagging, or that a delicate solar sail is perfectly tensioned. More than just a spectacle, this video becomes priceless engineering data, revealing the actual dynamics of the deployment in a way sensors alone cannot. It shows the gentle wobble of a panel as it settles, or the way shadows play across a new structure, providing clues for refining the next generation of designs. For the most ambitious and complex missions, we take observation a step further. A companion CubeSat, a tiny satellite no bigger than a loaf of bread, might be released from the main spacecraft. This small observer then drifts a safe distance away, turns its camera back towards its parent, and becomes an independent film crew. It captures the entire transformation from a unique third-party perspective, providing a complete, cinematic view of the self-assembly process that would be impossible to get from cameras on the unfolding structure itself. This external validation is the ultimate confirmation, closing the loop on years of digital modeling and ground testing. It turns a theoretical blueprint into a confirmed, operational asset in the harsh reality of space. With its form verified and its systems alive, the newly unfolded machine can now turn to its primary purpose, beginning with the most fundamental need for any structure in the void: generating power. The silent, sprawling wings of a spacecraft are its lifeblood, and origami has shattered every limit we once knew. These are not the rigid, limited panels of the past, but vast, fabric-like membranes that blossom from a container no larger than a suitcase. They use folding patterns with names like Miura Ori, a geometric marvel where a single, continuous motion can unfold an entire array. This pattern allows a surface the size of a football field to be compressed into a package small enough to fit in the trunk of a car. The result is a torrent of electrical power, an order of magnitude greater than anything previously possible. This newfound energy is the key that unlocks the next tier of space capability. It fuels powerful transmitters that can send back torrents of scientific data from the outer planets. It runs sophisticated laboratories and advanced imaging systems that would have starved for power just a decade ago. It extends mission lifetimes from years to decades, turning fleeting visits into enduring presences around distant worlds. This leap in power generation is the essential foundation for humanity's most ambitious orbital dream: space-based solar power. The vision of capturing sunlight in the eternal day of space and beaming it wirelessly to Earth requires platforms of unimaginable scale, structures far too large to be launched in one piece. For these colossal energy farms, origami deployment is not merely convenient, it is the only physically possible way they will ever be built. This technology is already here, silently powering our global communications and peering into the deepest cosmos. But a powerful machine is a silent monument if it cannot speak, and here too, the fold works its magic. A massive, silent ear now blossoms in orbit, its precise parabolic form focused on a distant whisper. This is the realm of deployable antennas, where origami principles are giving our machines voices and hearing on an unprecedented scale. The fundamental rule of communication in space is simple, yet brutal: the size of your antenna is everything. A larger dish can collect fainter signals from the edge of the solar system, and it can transmit vast streams of data back to Earth with pinpoint focus. For decades, we were constrained, forced to use small, rigid antennas that limited our conversations with the cosmos to a slow, quiet murmur. But by treating these colossal dishes as intricate works of folded engineering, we have shattered that constraint. Engineers design these reflectors from advanced, flexible meshes or gossamer thin membranes, materials that can be meticulously pleated and rolled into a compact cylinder no wider than a rocket fairing. The deployment is a masterpiece of controlled motion. Through a combination of strain energy and gentle motorized guidance, the packed membrane unfurls. But it does not just flap open, it pulls itself taut into a perfect, mathematically precise curve. This curvature is not an approximation, it is engineered to microscopic tolerances, because every millimeter of that parabolic shape is critical for focusing radio waves with the absolute clarity needed to hear a probe from Jupiter or send a high-definition video feed from a spy satellite. The result is a high-gain antenna, a term that simply means a supremely focused and powerful instrument for talking and listening. This single innovation is the backbone of our modern connection to space. It enables the torrents of scientific data flowing from the Mars rovers, the crystal-clear imagery from Earth observation, satellites that monitor our planet's health, and the burgeoning mega-constellations that aim to blanket the globe in high-speed internet. We are no longer just whispering into the void, we are having a clear, high-bandwidth conversation across the solar system. And just as we have built a giant ear to listen, we are now forging an equally enormous eye to see. The same folding principles that grant a spacecraft its voice now forge an eye of unprecedented power. To peer deeper into the cosmos, to witness the first starlight and directly see worlds orbiting other suns, we must build mirrors of staggering scale. The iconic golden hexagons of the James Webb Space Telescope represent a monumental leap, a segmented mirror that journeyed to space in a tightly packed bundle and then performed a slow, precise ballet to lock into a single, perfect surface. Yet this is merely the beginning. The next generation of observatories, concepts with names like LUVOIR and HAB-X, demand primary mirrors spanning tens of meters, colossal structures that would be utterly impossible to launch as one piece. Their creation hinges entirely on the art of cosmic origami. The challenge is breathtakingly complex. It is not just the mirror itself that must fold, but also the enormous, multi-layered sunshield that protects the telescope's delicate infrared instruments. This sunshield is a feat of engineering in its own right, a gossamer thin barrier the size of a tennis court that must deploy without a single tear or snag, creating an island of profound cold in the blazing heat of the sun. Every crease in its membrane, every hinge on a mirror segment, is a calculated risk that must be engineered into absolute certainty. The reward for this intricate dance of unfolding parts is a window into the unknown. These astronomical origami machines will have the resolution and sensitivity to directly image pale blue dots orbiting distant stars, analyzing their atmospheres for signs of life. They will gaze back in time to capture the light of the very first galaxies emerging from the cosmic dark ages. This is the ultimate purpose of the fold, to build stable, silent platforms in the void from which we can question the universe itself. The quest for a perfectly stable view leads to another profound application, one that relies on the same principles to create a new kind of orbital foundation. A tightrope walker's long pole is a perfect analog for stability in the void, and this is the precise role of the deployable boom. Many of our most ambitious space missions demand a rigid, extended structure to separate sensitive instruments from the main body of the spacecraft. A magnetometer designed to measure the faintest cosmic magnetic fields is useless if it is sitting next to the spacecraft's own electronics, which generate magnetic interference. It needs to be held out at a distance on a long, stable arm. This same principle applies to keeping delicate optical lenses and sensors clean, positioning them far away from the contaminating plumes of the spacecraft's own thrusters. The solution, once again, comes from a fold. Engineers have created booms that launch as flat, coiled tapes or slender strips, packed away with incredible efficiency. When the command is given, they unspool or unfold, often locking into a rigid, tubular truss structure that is both remarkably strong and incredibly lightweight. This transformation from a two-dimensional ribbon into a three-dimensional beam is a classic piece of origami engineering. These booms form the essential skeleton for complex orbital operations. They can deploy large radar antennas, create the stable, long baseline needed for interferometry, where multiple small telescopes work together to mimic the power of one giant one, and they can even form the primary backbone for a future space station module, defining its shape and providing the framework to which everything else is attached. Their reliability and compact stowage make them the unsung heroes of the orbital revolution, the rigid bones upon which the muscle and nerve of our technology are mounted. With such a stable and versatile foundation now possible, our vision can expand from constructing mere machines to engineering the very spaces where humans will live and work among the stars. The true test of this unfolding revolution lies not in the machines we send, but in the homes we build around them. The ultimate expression of orbital origami is the creation of human habitable volumes, transforming cramped metal cans into spacious, livable environments. Private companies are already pioneering this future with inflatable habitats, a brilliant hybrid approach. These modules launch as incredibly dense folded packages, little more than tightly rolled cylinders. But once in orbit, they undergo a second birth. They are inflated, not with air like a simple balloon, but with a controlled mixture of gases, expanding to create living and working spaces that dwarf the interior of any traditional, rigid module. Imagine the difference between living in a small closet and walking into a multi-room apartment, all from a launch package of the same size. The walls themselves are technological marvels. They are complex, multi-layered structures, often woven with fabrics stronger than steel. Embedded within these layers are origami-like reinforcements, rigid foldable panels that snap into place during inflation to provide essential structural strength. This layered shield is meticulously designed to protect inhabitants from two of space's greatest dangers: the relentless hail of micrometeorites and the insidious barrage of cosmic radiation. Looking further ahead, this concept scales to an incredible degree. Visionary plans for entire space stations or lunar bases involve prefabricated segments, entire rooms, and connecting corridors that are folded flat for launch. Upon arrival, they would autonomously unfold and assemble, locking together to form large, interconnected structures under the guidance of robotic systems. This approach is a complete game changer. It could dramatically reduce the cost and complexity of building sustainable human outposts on the Moon, Mars, or in the deep space between worlds. Instead of requiring dozens of expensive, dedicated rocket launches to ferry up small, rigid pieces for astronauts to painstakingly bolt together in risky spacewalks, we could send entire habitats in a single flight. This is not just an improvement in efficiency, it is the key that makes the dream of a continuous, growing human presence beyond Earth an achievable reality. But as these structures grow from single modules into entire orbital villages, a new question emerges. How do we build the truly massive frameworks that will support them? A roll of material and a robotic arm now replace the pre-folded satellite. This is the next evolutionary leap, where the Orbital Origami Revolution transitions from deployment to true in-space creation. We are moving beyond simply unfolding what we built on Earth and toward building entirely new things in the void itself. Picture a compact orbital factory, a spacecraft equipped not with a single folded structure, but with raw, advanced materials and a suite of 3D printers and nimble robotic assemblers. In the calm of microgravity, this factory would use the principles of folding to transform flat sheets of composite material into large, rigid trusses and complex panels. Robotic arms, guided by sophisticated algorithms, would then slot these components together, building structures of a scale that is simply unimaginable for any single rocket launch. This process completely shatters the last remaining link between a structure's ultimate size and the dimensions of a rocket's fairing. The size of what we can build is no longer limited by what we can fit inside a cylinder, but only by our ambition and the resources we can ferry up. This decoupling unlocks projects that sound like science fiction. We could construct a radio telescope with a dish spanning kilometers, an instrument so vast it could listen for the faint echoes of the universe's birth. We could assemble massive solar power farms, their wings stretching for miles, harvesting sunlight with phenomenal efficiency. We could even build rotating space habitats, enormous wheels that spin to create artificial gravity, offering a true home for long-term living in orbit. This is the ultimate culmination of the folding principle, where the space environment itself becomes our workshop, and the act of folding is the fundamental process of all construction. As we stand on the brink of building these colossal creations, we must also look ahead with a sense of profound responsibility. considering the long-term impact our expanding orbital footprint will have on this new frontier. A vast, silent solar array presents a magnificent target in the orbital shooting gallery. The very act of unfolding these colossal structures creates a fundamental new vulnerability, dramatically increasing their cross-sectional area and the statistical probability of a catastrophic collision with the countless fragments of space debris whirling around our planet. This is the unavoidable trade-off of the Orbital Origami Revolution, a direct consequence of its own brilliant success. Each new football field-sized antenna or sprawling habitat module adds to the congestion in increasingly valuable orbital pathways. A single impact with a piece of debris no larger than a screw, traveling at 10 times the speed of a bullet, can instantly shatter a critical component. Worse, such a collision does not just disable a single satellite. It can generate a devastating cloud of new, high-velocity fragments, each one a potential weapon capable of triggering a chain reaction of further destruction in a scenario known as the Kessler syndrome. This nightmare cascade could render entire orbital regions unusable for generations, trapping us on our own planet. The long-term reliability of the folding mechanisms themselves becomes a primary line of defense against this future. A single stuck hinge or a failed motor on a large structure could leave it stranded and uncontrollable, transforming a billion-dollar asset into a massive, unguided hazard for decades. This is why the engineering focus extends far beyond a successful deployment. It must guarantee a stable, predictable existence for the entire multi-year lifespan of the mission. But the ultimate test of responsibility comes at the very end of a spacecraft's life. The same origami principles that gave it form must now guide its final exit. Responsible design now mandates a clear path for end-of-life disposal, turning potential hazards into controlled departures. One elegant solution uses the technology in reverse. A satellite could be designed to refold its large arrays and antennas, dramatically reducing its drag profile and allowing it to be steered into a precise, controlled deorbit burn over a remote ocean area. For satellites in higher orbits where a powered re-entry is not feasible, engineers are incorporating a final, simple fold, the drag sail. This ultra-lightweight membrane, stowed for years in a tiny package, can be deployed at the mission's end. Though thin as tissue paper, it billows out to catch the wispy tendrils of the Earth's upper atmosphere, creating just enough drag to slowly but surely pull the spacecraft down to a fiery, safe demise decades ahead of its natural decay. This is not an optional feature, it is becoming a core tenet of modern space law and ethical engineering. The Orbital Origami Revolution, therefore, carries with it a profound responsibility. Its promise of building bigger and bolder in space is inextricably linked to our collective duty to keep that space accessible and safe. The final fold must always be the one that cleans up after itself. Every dollar saved on a rocket launch is a dollar invested in the future. The relentless economic pressure of spaceflight is the true engine behind this unfolding revolution, because launching anything beyond our atmosphere remains one of the most expensive endeavors humanity undertakes. The price tag is staggering, often sitting at tens of thousands of dollars for every single kilogram you need to lift into orbit. For decades, this brutal math forced a difficult choice. You could either send a small, capable machine or dream of a large, powerful one. Origami technology shatters that compromise. It is not about making rockets cheaper, though that effort continues in parallel. It is about making every cubic centimeter inside that rocket work harder. By packing vastly more capability into the same expensive launch volume, origami dramatically increases the value of every mission. Think of it as the ultimate form of cosmic efficiency, a way to cheat the fundamental constraints of the rocket equation itself. This single breakthrough is what transforms science fiction into a business plan. It makes the economics of a private space station suddenly plausible, where large, comfortable inflatable modules can be launched in just a few flights instead of dozens. It is the foundational technology behind the mega constellations of communications satellites, where thousands of foldable nodes are packed into a single launch to blanket the Earth in internet connectivity. For scientists, it means that a flagship observatory, once deemed too large and too costly to ever build, can now be designed to fit within a manageable budget because its colossal mirror and sunshield can be folded into a single, launchable package. This is not just an incremental improvement, it is a complete redefinition of what is possible. The economic viability of these projects creates a powerful feedback loop. As new markets open, investment pours in, accelerating research and development into even better folding techniques and smarter materials. This virtuous cycle of innovation pushes the entire industry forward at a breathtaking pace. The potential for profit is driving this revolution as much as the pursuit of knowledge, establishing a new commercial frontier in low Earth orbit and beyond. This economic imperative, however, is not unfolding in a vacuum. It is creating a new arena for international competition and collaboration, where technological leadership in space is increasingly synonymous with strategic influence on Earth. The silent expansion of a satellite's wings is a display of national capability. This unfolding revolution in space technology has ignited a quiet but determined race among the world's leading space powers. Agencies like NASA in the United States, the European Space Agency, JAXA in Japan, and China's National Space Program are all pouring immense resources into perfecting the art of the fold. Why such intense focus? Because the nation that masters self-assembling space systems gains a profound strategic edge. The ability to deploy the largest communication antenna, the most powerful spy satellite, or the most sensitive Earth monitoring platform directly translates into advantages in global connectivity, intelligence, and environmental security. This is a high-stakes competition where technological leadership in orbit translates into tangible influence back on Earth. Yet, for all this competition, there exists a powerful countercurrent of collaboration. The International Space Station stands as a monumental testament to what nations can achieve when they combine their expertise. Its very structure, a complex patchwork of modules from different countries, is a masterpiece of international engineering, relying on precisely the kind of deployment and integration skills that folding technology demands. This collaborative spirit is the likely blueprint for humanity's next giant leaps. A future lunar gateway station or an interstellar telescope with a mirror the size of a city block will be too vast, too complex, and too expensive for any single nation to build alone. These mega projects will demand a global consortium, pooling the best folding techniques, the smartest materials, and the most reliable deployment mechanisms from laboratories across the world. The Orbital Origami Revolution is therefore unfolding on a dual track. It is both a race for individual advantage and a necessity for collective survival and exploration. This dynamic, this constant tension and cooperation, acts as a powerful engine for innovation. Every breakthrough in one nation's lab pushes all the others to reach further, ensuring that the boundaries of what we can build in space are being redrawn at an exhilarating pace. A folded paper crane on a classroom desk is a silent lesson in cosmic engineering. This elegant connection between a simple art and the complexities of space is sparking a revolution in education itself. The Orbital Origami Revolution is not just building machines, it is building the minds that will one day design them. Educational programs around the world are seizing on this powerful link, using paper models to teach the fundamental laws of geometry, the principles of structural stability, and the real-world challenges of mission design. Students are not just learning theorems, they are folding them, feeling the creases that create strength from a flat sheet, and seeing how a single kinematic motion can transform a two-dimensional pattern into a complex three-dimensional object. This hands-on experience makes abstract mathematical concepts tangible and unforgettable. The inspiration does not stop in the classroom. University-level competitions push this understanding to its limits, challenging teams to design, build, and test their own deployable structures. These are not theoretical exercises. They are demanding projects that mirror the exact engineering dilemmas faced by professionals at NASA or the European Space Agency. Students grapple with the same questions of material selection, deployment sequencing, and system reliability, forging a new generation of engineers who think in folds and creases as naturally as their predecessors thought in bolts and beams. This technology acts as a brilliant gateway, attracting young minds to science, technology, engineering, and mathematics by demonstrating a profound shift. It shows that the future of engineering is not solely about incremental improvements, making metals stronger or processes faster. It is about a paradigm shift toward smarter, more elegant, and almost biological forms of design. It proves that the most powerful solutions can be beautiful, efficient, and inspired by the natural world. The path to the stars these programs teach can be as graceful and intentional as a piece of folded art. This cultivation of inspiration is not a secondary benefit, it is a critical investment. The ultimate applications of this transformative technology, the interstellar probes and rotating space cities, will be conceived and built by the students who are today folding paper in their classrooms. We are not just teaching them how to build, we are inviting them to imagine what to build, planting the seeds for a spacefaring civilization whose full shape we can only begin to glimpse. A sail made of light itself now billows in the silent ocean of space. This is the most poetic expression of the Orbital Origami Revolution, where the art of the fold becomes the engine for our journey to the stars. Solar sails and light sails are not spacecraft in the traditional sense. They are ethereal vessels that ride on the gentle, continuous pressure of photons. Sunlight, though it has no mass, carries momentum, and when countless photons bounce off a vast reflective membrane, they impart a tiny, unending push. Over days, months, and years, this minuscule force accumulates, allowing a craft to achieve tremendous speeds without a single drop of fuel. The grandeur of this idea is matched only by its physical demands. To catch enough of this phantom wind, the sail must be colossal, often spanning square kilometers, yet it must be thinner than a human hair and lighter than a feather. Constructing such a thing is one challenge, but launching it is another matter entirely. It is here that origami proves not just useful, but utterly essential. Without the ability to meticulously fold this city-sized sheet of impossibly delicate material into a container the size of a dishwasher, the entire concept would remain a beautiful fantasy. Missions on the near horizon, like NASA NEA Scout, are turning this fantasy into operational reality. This small spacecraft will journey to a near-Earth asteroid, propelled solely by its neatly packaged solar sail, which will unfurl to reveal a surface as large as a racquetball court. But this is merely a first, timid step onto the cosmic beach. The true interstellar dream is embodied by concepts like breakthrough starshot. Its vision is as breathtaking as it is audacious, to send a fleet of tiny, gram-scale probes to our nearest stellar neighbor, Alpha Centauri, within a human lifetime. For this to work, the light sail attached to each microscopic probe must be a masterpiece of folding engineering. It must deploy with absolute perfection, forming a flawless, flat reflector that can be pushed not by sunlight, but by a massive, focused laser beam from Earth. The slightest wrinkle, a single misaligned fold, would scatter the laser's energy and send the probe tumbling off course into the eternal night. This represents the ultimate test of the fold, a process where millimeter precision on Earth translates into a successful 4-light-year journey. We are using the ancient art of folding to literally sail on beams of light, carrying the fragile weight of human curiosity across the interstellar void. Guiding such a delicate vessel on its epic journey requires a new kind of intelligence, one that must be woven directly into the fabric of the sail itself. A single misaligned fold in a solar sail could doom an interstellar mission. This level of precision demands a new kind of cosmic intelligence, one that can watch, react, and even think for itself. Artificial intelligence is rapidly becoming the indispensable partner in this unfolding revolution, the cognitive layer that will manage the breathtaking complexity of future space systems. These are not simple, pre-programmed deployments anymore. We are moving toward structures that build themselves from raw materials and robots that assemble entire stations. The sheer number of variables involved in such a process is far too great for any human team on the ground to manage in real time, especially with communications delays that can stretch to hours for deep space missions. This is where an onboard AI becomes the ultimate mission conductor. It will monitor the entire symphony of self-assembly through a constant stream of sensor data and live video feeds. Imagine a robotic arm in orbit tasked with slotting a large, folded truss into place. The AI's computer vision system would act as its eyes, analyzing the position of the truss down to the millimeter, guiding the arm with a steady, unerring hand that never tires and never blinks. If a component does not latch correctly, or if a motor reports an unexpected resistance, the AI does not panic. It cross-references the anomaly against a vast library of simulated scenarios and makes a decision in milliseconds. It might pause the entire sequence, gently reverse a movement, and then attempt the latch again with a slightly adjusted angle. It could command a backup motor to engage, bypassing a potentially faulty component entirely. This real-time problem-solving transforms a rigid, brittle sequence into a resilient, adaptable process. But the role of AI begins long before a rocket ever leaves the launch pad. In the design phase, machine learning algorithms are already proving invaluable. Engineers can set a goal for a structure, such as maximum deployed surface area with minimum stowed volume and 100% deployment reliability. The AI then gets to work exploring thousands, even millions of possible fold patterns. It tests them in digital simulations, learning which geometries are strongest, which sequences are most efficient, and which designs are most tolerant to tiny manufacturing imperfections. It can discover novel, counterintuitive folding solutions that a human designer might never conceive, pushing the boundaries of what is mechanically possible. This powerful partnership between human creativity and machine optimization is accelerating the entire field. As our orbital ambitions grow from single satellites to sprawling, interconnected orbital yards, this artificial intelligence becomes the central nervous system for the entire operation. It will manage the life cycle of these complex assets, from their initial unfolding through years of operational service, and even overseeing their final, responsible decommissioning. This cognitive layer ensures that the cosmic origami unfolding around us does so not just with mechanical precision, but with a resilient, adaptive intelligence, preparing our machines for the unpredictable reality of space. A billion-dollar mission gets only one chance to unfold correctly. That is why the most critical tests for these folding machines happen long before a rocket ever ignites, inside some of the most advanced laboratories on Earth. Engineers must answer a deceptively simple question. How will a structure designed for the weightless void behave when it is built and tested under the constant pull of gravity? The solution is as ingenious as the satellites themselves, a system called gravity offloading. Picture a vast, high bay room where a full-scale prototype of a massive solar array is suspended from an intricate overhead grid of pulleys and cables. These cables are attached to precisely calibrated counterweights, each one carefully set to cancel out the exact weight of the section it supports. The result is a delicate balancing act that effectively tricks the structure into behaving as if it were in orbit. It floats in a simulated zero-G, allowing engineers to observe the true kinematics of its deployment, free from the sagging and binding that gravity would otherwise cause. They watch for any hesitation in a joint's rotation, any unexpected flex in a boom, or any sign that two components might collide during their carefully choreographed dance. This terrestrial ballet reveals problems that pure computer modeling can miss, providing priceless data to refine the design. But passing this test is only the first hurdle. The real trial by fire, or rather by ice and vacuum, comes next. The complete system is then rolled into a cavernous thermal vacuum chamber, a steel giant capable of swallowing a city bus. The massive doors seal with a definitive thud, and the air is violently sucked out, creating a perfect vacuum, an environment as empty as deep space. Then the temperature extremes begin. Powerful banks of lamps simulate the unfiltered blaze of the sun, heating the spacecraft's surface to temperatures that would boil water. Then they are switched off, and liquid nitrogen floods through the chamber's walls, plunging the environment into a deep freeze colder than the dark side of the moon. Inside, the folding mechanism is commanded to deploy again and again over hundreds of cycles. Engineers are looking for any sign of weakness, any change in the material after repeated exposure to such brutal swings. Will a hinge pin made from a shape memory alloy still retract reliably on the 100th try? Will a composite panel begin to delaminate or develop tiny cracks under the stress? The entire process is often filmed with high-speed cameras, capturing every millisecond of the deployment in stunning detail. Played back in slow motion, this footage can reveal a minuscule wobble or a barely perceptible stickiness in a joint, issues that would be invisible to the naked eye but could spell disaster in orbit. This painstaking, iterative cycle of test, analyze, and refine is what transforms a theoretical design into a flight-proven certainty. It is the unglamorous, essential work that builds the unshakable confidence to entrust a unique, irreplaceable mission to the silent, automated unfolding of a machine in the void. A leaf unfurls from a tight bud with a silent, hydraulic grace that human engineers can only envy. This simple act is a masterclass in efficient deployment, perfected over millions of years of evolution. Nature was the original master of origami, long before we ever folded a paper crane. From the breathtakingly intricate unfurling of a butterfly's wing from its cramped chrysalis to the way a single strand of DNA packs an entire blueprint for life into a microscopic space, biology is filled with self-assembling systems. Scientists are now peering into this ancient library of designs, seeking solutions to our most complex space-folding challenges. The wing of an insect is a particularly powerful source of inspiration. Packed within its tiny larval case, a beetle's wing is a miracle of compact storage, a complex structure of veins and membranes folded in an elaborate, three-dimensional pattern that allows it to spring open rapidly and reliably for its first and only flight. Researchers are meticulously mapping these natural crease patterns, discovering geometries that are both incredibly strong and astoundingly space-efficient. These biological blueprints are directly inspiring new generations of solar arrays and antenna reflectors, guiding us toward fold patterns that are more resilient and pack even tighter than our best human-made designs. The lessons extend down to the molecular scale. Consider a virus, a seemingly simple entity that constructs its own protein shell or capsid by following an innate set of folding instructions. Individual protein subunits self-assemble into a perfectly symmetrical, hollow geometric structure, a process that is both spontaneous and precise. This natural programming offers a radical vision for future space construction, where we might launch a container of simple, identical parts that, once in orbit, are triggered to fold and lock together into a complex, large-scale habitat, all without a single robotic arm. This field, known as biomimicry, is not about copying nature outright. It is about learning the fundamental principles that make these biological systems so successful, principles of efficiency, resilience, and self-organization. By tapping into this deep well of proven strategies, we are accelerating our own engineering, creating a powerful synergy between the slow, brilliant intelligence of evolution and the focused, ambitious drive of human innovation. The very act of learning how life folds itself prepares us to one day build the folded structures that will sustain life itself among the stars. Bulky gloved hands, not just robotic arms, have long been the final step in bringing our folded machines to life. Even as we push toward full autonomy, the human mind and its capacity for improvisation remain a critical part of the equation. The International Space Station itself is a testament to this, a sprawling laboratory assembled piece by piece during countless spacewalks. Astronauts have acted as cosmic folders and unfolders in their own right, manually deploying radiator panels, releasing stubborn antenna booms, and connecting the electrical veins of new modules. Their role, however, is evolving. As the structures we build transition from single satellites to entire orbital yards, astronauts will shift from being primary assemblers to expert supervisors and maintenance crews. Think of them as the master technicians for these colossal origami creations. They will venture outside with specialized toolkits designed not for bolts but for folds. A joint on a massive solar array might report an anomalous strain reading, and an astronaut would be dispatched to inspect the intricate hinge mechanism, looking for signs of micrometeoroid pitting or material fatigue. They might apply a corrective torque with a powered wrench or replace a small, failed actuator, tasks requiring a judgment and dexterity that remain beyond even our most advanced robots. This reality forces engineers to design with the human touch in mind. Every latch must have a clearly marked, oversized handle that can be operated with a pressurized glove. Every critical joint needs a bright, unambiguous visual indicator, a green stripe or a pop-out pin, that instantly communicates a locked or unlocked status to a crew member floating outside. These are not minor details, they are fundamental safety and reliability features. This synergy between human ingenuity and robotic precision creates a powerful, resilient system. The robot can perform the repetitive, strenuous, or dangerous initial deployments, while the human stands ready to diagnose the unpredictable, solve the novel problem, and provide the gentle persuasion a stubborn mechanism might need. It is this partnership that will ultimately build and sustain the large-scale orbital infrastructure of the future, ensuring that our folded machines can be serviced, upgraded, and kept functioning for decades, turning temporary installations into permanent outposts. A machine that builds itself blurs the line between a simple tool and an independent agent. We are entering an era where the act of creation, once a uniquely human endeavor, is being delegated to autonomous systems. This shift forces us to confront deep philosophical questions about control, responsibility, and the very nature of the machines we send into the cosmos. When a satellite unfolds according to its own internal logic, responding to sensor data without a direct command from Earth, is it merely executing a complex program, or is it demonstrating a primitive form of agency? This is not just a technical distinction, it is a fundamental issue that will define our relationship with the technology we are creating. The concept touches on themes that have fascinated philosophers for centuries and fueled science fiction for decades. We are now building the very systems that once existed only in stories, and with that power comes a profound responsibility. The most immediate challenge is one of legal and ethical accountability. If an autonomous folding system malfunctions, misinterprets its environment, and unfolds in a way that creates a massive debris cloud or collides with another vessel, who is to blame? Is it the software developer who wrote the algorithm, the engineer who designed the hinge, the company that launched it, or the international regulator that approved the mission? Our current terrestrial frameworks for liability are poorly suited to these complex, decentralized chains of events happening in the global commons of space. This ambiguity creates a dangerous gap, one that could be exploited or could lead to catastrophic misunderstandings between nations. The need for clear, forward-thinking international treaties and norms has never been more urgent. We must establish rules of the road for this new class of self-assembling space asset, defining everything from minimum safety protocols for autonomous deployment to unambiguous lines of responsibility for accidents. This is not about stifling innovation. It is about building a stable and predictable environment where innovation can thrive without putting our shared orbital space at risk. Engaging with these questions now, while the technology is still in its relative infancy, is our best chance to ensure the Orbital Origami Revolution develops in a direction that is safe, secure, and ultimately aligned with our deepest human values. The path forward must be guided not just by what we can build, but by a clear vision of the future we wish to create. From the delicate crease of a paper crane to the silent bloom of a solar sail, this revolution redefines our cosmic ambitions. We are witnessing a fundamental shift in how we approach the final frontier, moving from brute force to elegant intelligence. This journey reveals a profound truth about human ingenuity, that our greatest leaps often come from connecting seemingly unrelated fields. The ancient art of paper folding, the modern miracle of materials that remember, and the silent logic of digital algorithms have merged to shatter the old limits. We are no longer constrained by the size of a rocket's nose cone. Our imagination is the new boundary, and it is a boundary we are constantly pushing outward. This synergy is already alive in orbit, powering our communications, guarding our planet, and peering into the depths of the universe. But its true promise stretches far beyond today's satellites. It is the foundational technology for journeys to other stars and for building sustainable homes on distant worlds. With every fold engineered into a spacecraft's design, we are not just packing a machine for launch. We are folding a piece of our future, a compact promise that unfolds into the framework for a multi-planetary civilization. The cosmos presents an infinite canvas of emptiness and potential. Armed with the timeless principles of origami, we hold the tools to fill that void with structures of wonder and purpose. We are just beginning to sketch our place among the stars. Let us know in the comments which application of cosmic origami captures your imagination the most.